Hello everyone and welcome to another AP Computer Science video. This set of videos is going to be the last topic in our course this year, which is a nice thing to hear. And we'll finish up with the topic of recursion. And this is a really powerful tool, though it is one that most programmers don't necessarily have to use. It's not a requirement, it is a strategy we can take based on the design of programming languages to make certain problems easier. And if you go further in programming beyond this course or on your own studies, you might see there are situations where some problems lend themselves to a particular type of thinking. And we'll talk about the typical thinking that most of us deal with when programming is the iterative approach, right? Going step by step, repeating ourselves. Loops or iterations. So using loops is a common solution for most situations. But the recursive approach or approach that uses recursion is another style of solving problems that for some problems it manages to be a little bit easier to write. And the main thing we can take away from all of this is that though recursive solutions do work, they're not necessarily the most efficient, though they are often simple to write. So the code may seem like it's less code, though they might be just or more expensive in terms of computation. So it's a matter of decision making and is it worth the time, is it worth the effort, even though the code is much easier to read. So that's one advantage that we'll see. And so we'll do some examples, both an iterative approach to something and a recursive approach, and we'll talk about what that means and why you might use one or the other. With all that said, on the AP exam, you will not have to program your own recursive solutions. Instead, you will be given code that is recursive and understand how to read it and interpret what the result would be. I'm of the mind that if you understand recursion, you could probably program most of the problems and read them, but on the exam, you're never going to be forced to use recursion in a solution. You might be shown a solution that has recursion in it and understand what it means, but beyond that, you won't be forced to code it. So let's do some examples. I'm going to make a new package, our last package here, and we'll call this the recursion package. We'll do lowercase r. So there's recursion. Let's pick a new class, and we'll call this examples. We'll start off with some small examples. So we'll make a main, like we always do. There it is. And so before we do the recursive solution, we're going to talk about one kind of famous problem, which you might know the definition of, and maybe you've not heard the word, but if you've done any kind of math in high school, you've probably seen this operation and understand what it is, and then we can talk about why it can be implemented in two different ways. And so what I'm talking about is the factorial operator in math. So if we say something like 4 factorial, right, I'm going to put it in comments, right, so we'll say factorial. 4 factorial, exclamation point usually means factorial. We're saying that this is the answer is that number times the next number lower than it times the next number lower than that one, and so on. So 4 times 3 times 2 times 1. So we can say that 4 factorial is the same as 4 times 3, which is 12, times 2, which is 24, times 1, which is 24. Right? So we know that 4 factorial is 24. 3 factorial is 3 times 2, which is 6. Right? And so on. So we can go from any factorial and figure out what the result is. And if we do any other factorials, larger or smaller, it's just more multiplication. We can probably generalize this formula. So what we can say is, well, if we have n factorial, we can say it's the same as n times n minus 1 factorial. So if n is 4, then we're saying the answer to 4 factorial is 4 times 3 factorial. And then 3 factorial can be defined as 3 times 2 factorial, and so on. The result is that it kind of does this. And so really this is something that, even though maybe in math it makes a lot of sense, the reality is we are defining the operation by using the operation. And this doesn't really make a lot of sense. This is like trying to, if someone asks you to give you a definition of a word, you can't really, most people would agree that you can't define a word by using the word in the definition. It's kind of a very odd situation. But the idea is that the reason this works for factorial and the reason this works in general for recursion is there is one key factor, is that there has to be some special situation where this definition no longer applies, but a much simpler one applies. And we'll say, in this situation, n factorial is defined as n times n minus 1 factorial, where where if n equals 1 or n equals 0, n factorial is equal to 1. Right, so we're basically saying this is true for most situations, but if n happens to be 1 or 0, then the answer is just 1. And then if it's negative, it doesn't count at all. So we can put that definition. There is no negative factorial. It's not possible to get. And so the idea is that we could really define things, certain things can be defined in a way that can use itself in its definition, but it relies on the fact that there is some fact about it that eventually does not have that definition. In this situation, the factorial of 1 or 0 is an immediate answer. There is no step where we have to look at the definition again. And this is what recursion boils down to in our code. So before we get to that point, let's go ahead and implement this without recursion. Right? We basically said, well, if it's 4, it's the same as saying 4 times 3 times 2 times 1. If it's 10, it would be 10 times 9 times 8 times 7, and so on. So if we can see that pattern, a loop could do this for us. So let's make a method for factorial that's iterative and solves the problem. So we're going to say public, and we'll use ints for now, though factorials can get very large very quickly, so theoretically we could run out of space in our data type if we went too large. But we won't do that for now. So we'll say public int, let's do static int because we're going to use this in our main. We'll call it fact iter for the factorial iterative, and our input is simply n, right? So you give us n, and we return the factorial of n. And so think about it for a moment. Given this solution, what could we do with a loop to make this happen? So if you've tried it on your own, hopefully you come up with a solution that works for all situations. We can simply say, we'll say that our answer is equal to 1, and we can say for int I equal to 0. Actually, we don't even need to do that, but we can start off with 1 I less than n, inclusive of n, I plus plus. We can say answer times equals I. And let's see if that's correct. Sorry, not I, but answer. There it is. So let's go ahead and try doing this out. So we'll say int fact is equal to, and let's do fact iter of 3, which we know should be 3 times 2 times 1, which should be 6. Let's print it out and see if that's correct. Maybe I did my implementation wrong, but if not, we should get 6 as an answer. Let's run it and see what happens. We are inclusive of 3, because otherwise we would not multiply. And there it is, 6. Let's make this a little bit, and then let's try it with a bigger number. Let's try 4. We had said factorial of 4 was 24. Well, let's see, there it is. And let's do one last one. Again, the problem is if we do it too large, it might get really large really quickly. 10 factorial is a pretty big number. That's a very, very large number. That's 3 million already. If I do any more, it might actually run out of space. So if I do like 15, if it goes over 2 billion or 4 billion, there it is. So it's close to, that's a huge number. Let's try one more. Let's do 18, and we'll see that we're going to end up potentially with a negative number because of the overflow of our answer. Integers can only go up to positive 2 billion and change, so that the factorial of 18 is much too large to fit in an integer. We could use the long data type for 2 to the 32 as a much larger size possible for our thing, but we're going to stick with that for now. But there it is. It does work for any of these numbers. But this is the iterative approach. There's no recursion. There's no defining the method or the functionality with its own. So now let's try doing factorial recursively. Recursion always takes 3 steps, so we're going to put some notes here. Recursion requires 3 steps. Right? And again, I say steps, but in reality, it's just 3 things that must be true. And they're usually in some particular order, but the order is not always guaranteed. So I don't know if it's steps is the right word, but 3 components. We'll say components. The first is what's called a base case. Base case, right? A situation where the answer to the problem is immediate and no longer requires recursion. That means that the answer is immediate. So in the case of factorial, the base case is if n is less than or equal to 1. So in reality, I'm going to ignore negative numbers, so we'll just handle the base case of positive numbers. So if the answer is 1 or 0, we know the answer is immediately 1, and we won't go any further. If it's negative, we could maybe throw an exception or crash the program saying you can't have negative values, or we could just return the answer of 1, though I don't think that's really true when it comes to the mathematics of it. But our base case is situation where the answer is known without recursion. Right? Step 2 is simplify the problem. Or component 2 is simplify the problem. The reality is that each step, every time we try to recursively solve it, every time we're trying to solve the problem with our own definition, it cannot be on the same problem. You can imagine, and then so what is the simplification of this problem in factorial? If we notice it, we're saying that the factorial of a number n is n times a smaller factorial. Notice how n goes down by 1. So eventually, this definition will kind of decay into one of the base cases. So simplify the problem does not mean get smaller. It could mean get larger. It could mean divide by half. The purpose of simplifying the problem is to change the problem in a way that eventually it will end up at a base case if you have one. I also mentioned base cases. There's not always one base case. Sometimes there are multiple base cases. So it really depends on what the goal happens to be. So in this case, simplifying the problem is change the problem so that the recursion eventually reaches a base case, right? And the last step, or a component, is the recursive call, right? The method must call itself. That's the big trick. This is what seems very odd. Again, it's like, how can a method that you're defining call itself? How can you use something that hasn't been even being implemented? And that's the kind of trick of the whole problem. It's kind of strange, but what we can do is to make this work better in our minds, or make us believe that it's going to work, is make the assumption that when you call your recursive method, that it gives you the right answer. And if it gave you the right answer, then would the rest of everything make sense? So we can come up with this example in our implementation when we do our factorial. So let's try this out. So we'll say the recursive call of this method, the method must call itself. Those are the 3 steps. So let's make a method for factorial. We'll say public static int factorial. We'll call it fact recursive, or rec, and our input is still just a number n. So again, thankfully with recursion, with factorial, it's a very, very simple problem. We know the base cases, and we know the recursive call, and we know the simplifying of the problem, shrinking it. So typically we ask questions about the base cases first because they're easy to catch and stop. Either we return something or the program ends or something like that happens. And so we can say simply, well, if n is equal to 1 or n is equal to 0, then we know our answer is immediate. There's no recursion. The answer is 1. Right? This is the base case. Again, we're going to ignore negative numbers for now. Right? A proper implementation maybe would cause the program to give an issue if there were negative values. But here we'll say, you know what, if you give me 1 or 0, the answer is 1. No recursion necessary. And now here, in this situation, I can merge the simplification and the recursive call together. And this is what's going to happen. So our answer, if it's not the base case, is to recursively solve the problem. We're going to say, just like what we set up here, the answer must be n, whatever the current in n is, so in this case n, times n minus 1 factorial. So this is a method on our part. Our method is called factRec. But now, that's the recursive call. It's calling itself. And then here is the input, is the simplified problem. In this case, simplifying the problem is merely saying n minus 1. N minus 1. And there it is. Right? This may seem odd, right? I'm calling factRec inside of itself. But the claim is, let's pretend, let's say we were doing 5 factorial. We're saying the answer to 5 factorial, since it's not 1 or 0, is 5 times the recursive call on 4 factorial. So let's pretend they gave us the right answer. 4 factorial would be 24. 5 times 24 would be 120, and that is the correct answer. Therefore, the recursion on 5 factorial works. So if we assume that this works properly, pretend it's going to work, is the result we get the correct answer for the whole thing, then that means the recursion must make sense. So in this situation, we're saying, you know what, it is n times. So we've merged the recursive call and the simplification into one line. Sometimes it happens like that, sometimes it doesn't. It really does depend on what's happening. Now let's go ahead and try this out. Let's do int rec is equal to fact rec of 4. And let's print out the answer and make sure that it is in fact correct. Let's run this and see what happens. And there it is with 24. Let's change this one to 5. We should get 120. And there it is. Some things we need to note is that every time the method's called on itself, it's like the new version of the method's called, so the n is different for each time. These are called stack frames, where each time the method is called with a different n, they're not the same. I mean, they're the same method being called, but they're not the same method being run. It's like different copies of the method, and eventually they get to the bottom base case, and then they start kind of sending back their answer. The returns kind of pile up, and then start returning their answers, and the result is that the final return gives you this answer. So what would happen is, let's say we did 3 factorial, we'd say, okay, is 3 equal to 1 or 0? No. Then return 3 times the factorial of 2. Now we're here, n is 2. Is 2 equal to 1 or 0? No. So then we're returning 2 times the factorial of 1. So now we're here again. Is 1 equal to 1 or 0? Yes. So the answer is 1. So we came back up here, now we're at 1. 1 times 2 is 2. That returns, so now we're back where n is 3. 2 times 3 is 6. The answer is returned as 6. So that's how it kind of boils down to the simple base case and then kind of reverses itself back up to the answer. So there's our implementation of the factorial as a recursive method. We'll do one more example here, and again, this may be an example of something you've heard of, and the reality is it is commonly implemented, at least naively, with a recursive solution, though it is not very efficient, and we're going to draw a diagram that kind of shows why this is not efficient, and we'll see. We're going to try to implement a method that gives us the Fibonacci numbers. If you don't know what the Fibonacci numbers are, they're a set of numbers where the Fibonacci sequence begins with 2 ones. So if we say, what's the first Fibonacci number? We'll say that is the first Fibonacci number. That's the second Fibonacci number. Every subsequent Fibonacci number is generated by the sum of the previous 2. So the third Fibonacci number is the sum of the first 2. So 1 and 1, the third one becomes 2. The fourth one is the previous 2, so 1 plus 2, which is 3. The fifth one is 2 plus 3, which is 5. The sixth one is 3 plus 5, which is 8. And so on. 5 and 8 is 13, and it goes from there. So we can say, if you give me the 37th Fibonacci sequence number in the sequence, we could do that result. Now again, our recursive implementation will not necessarily be the most brilliant, and in fact will be very inefficient in terms of what it does, but it will potentially give us the answer, though it may take forever if we put too big of a choice. The reality is that recursion sometimes is not the best solution to certain situations, but we'll try this out for small sets of Fibonacci numbers. So here we go. Let's do this. Public. We'll stay static again. We'll say int because we're going to just assume integer values, and we'll call it Fibonacci. Our input is a number, which is the which one. It's not an index, so it's not like the 0 Fibonacci, the first one. It's the n, like the first one. So if n is 1, and so and we'll go ahead and say that's our answer. So here, what is the base case? What are the situations, or maybe more than one base case, where we know the answer immediately? And the answer is, if we give you the first or second number, the answer is always 1. The first 2 are always known to be 1 and 1. So let's handle that base case very simply. If n is equal to 1, or n is equal to 2, so if you ask for the first or second Fibonacci number, then the answer simply is 1. That's very convenient. And now otherwise, we can say, if I'm looking for the third one or fourth one, so the third one we'll say is the sum of the first and the second. The fourth one is the sum of the second and the third. The fifth one is the sum of the third and the fourth. So you notice that if I ask for the nth one, it's the sum of the nth minus 1 and the nth minus 2. So that means that's how we can implement it. So we can say, otherwise return the recursive call of the nth minus 1 number plus the Fibonacci of the nth minus second number. Again, we don't know which one they're going to ask for, so we can't say we know the answers. We can't just like assume the values. So we have to recursively get the answer to this one, and recursively get the answer to this one, and then add them together. So let's see if this does work, and then we'll see why this is inefficient when we draw a little diagram. So let's go ahead and try this. We'll say and fib is equal to Fibonacci, and we'll start off with the second one, which we know should be 1, and let's print out fib. We should get 1, and there it is, 1. Let's try doing the third one. which should be 2, because it's 1 and 1, which is 2. Make this a little bit bigger. And now that's the third one. Let's do the fourth one. And there it is, 1 plus 2, which is 3. Let's do the fifth one, which should be 5. And then let's do the sixth one, which should be 8. And there it is. And let's do the seventh one, which should be 13. And there it goes. And now I'm going to show a bigger number. Let's go ahead and do the 15th. 610, right? So again, let's do 20th. I know at some point it's going to slow down. Okay, that was pretty good. Let's do the 30th Fibonacci number. Let's see if it gives us that one. Not terrible. Let's do the 50th Fibonacci number. Ah, now suddenly it's taken a bit of time. And so our question is, why is it so much slower now? It's not. The other ones were pretty much immediate. But now at 50 numbers, which is really not that many numbers, it's significantly slower. Now, is it going to finish? I don't know. I'm probably going to have to stop it because I don't know how long it'll take. I haven't run it before that I remember of how long it's going to take to get the 50th number. We did 30 and it was pretty much instantaneous. Let's go ahead and do like 35th and see if it gives us that number quickly. That was pretty quick. Let's do like the 40th and let's see how long it takes. The 40th, it was pretty quick. Let's do the 45th and see how long it takes. Ah, now we're pushing it. Already at the 45th. Okay, it finished. That was pretty quick. 3 seconds though, that's kind of a little bit of time. Let's do one more. Let's do the 47th. That's 2 more numbers. And let's see how long that takes. It was 3 seconds before, and we went 2 numbers up. And in fact, it was so large it went out of bounds, and it took 7 seconds. So this isn't. We can't even get it. We have to use longs or some other data type to make this effective. So unfortunately, we can't even get the real answer. But that's okay. The point is that it does definitely take some time to make this happen. So now, like, how is this the case? How do I know that this was going to be inefficient in the first place? So let's go ahead and think about that for a moment. So let's open up our whiteboard. Let's look at this example through a diagram that we can see. So we'll say that we tried to solve, and I'm going to start here, the Fibonacci, and let's say the fib of, let's do like, I don't know, the 8th number. And so we'll see how big this goes. So the 8th, so we know that the solution to the Fibonacci sequence according to our definition, we ask, is it the base case? Is it the first or second? No. Then we know that we must solve this by getting the summation of the fib, I'm just going to call F from now on, of the 7th plus the fib of the 6th, right? The 2 previous ones, the 7th and 6th, right? But now, what is the solution to the 7th? Well, we need to know it is the fib of the 6th plus the fib of the 5th. And what is the solution to the Fibonacci of the 6th one? Well, it's the solution of the 5th plus the 4th Fibonacci number. And so the 6th, notice we already know what the 6th is. This one is going to be the Fibonacci of the 5th plus the Fibonacci of the 4th. And what is the 5th? It's the Fibonacci of the 4th plus the 3rd. Oof. And then how about the 5th? Same thing. The Fibonacci of the 4th plus the Fibonacci of the 3rd. And the 4th is the Fibonacci of the 3rd plus the Fibonacci of the 2nd. And again, I can keep going. And so notice that the 5th, the 4th, the 4th, and the 3rd have already been solved over here. And then now, so here we'll get to this one. We know the answer to the second one is 1. So this one stops. This one is the Fibonacci of the 2nd plus the Fibonacci of the 1st. We know these answers are 1 and 1. So there's 1 and there's 1. And then we know this one is the same thing as the Fibonacci of the 2nd plus the Fibonacci of the 1st, which we know is 1 and 1. And then this one is the 3rd and the 2nd, which we know is 1. So you can see how I'm being very repetitive. You'll notice that for any section, a lot of it has already been done somewhere else. You can see the 7th included the 6th and the 5th. So why did I solve the 6th on its own, and which is the 5th and the 4th? But I already got the 5th and the 4th for this one. I did it twice. So you'll notice the deeper I go in this giant tree, the quicker we end up doing the same math again and again. So you can imagine when I did 45th, how much we'd have to zoom out to see this gigantic tree of all the solutions. It would be just ridiculous. And so this is the main reason this is inefficient. We can see sections that are repeated. This whole thing, from here all the way to here is basically a repetition of what this one would be. And this section right here, which is this whole tree, is a repetition here. And the fourth one is this one and here. And this, so like we're doing the same work many, 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 many times over. So this is very inefficient. This is why this is a terrible implementation, even though it is a recursive implementation of the Fibonacci sequence. If we do the same diagram for the factorial, it's a little bit better. So if I do factorial, and I did the fifth, the factorial of the fifth we know is going to be 5 times the fact of the fourth, right? And we know the factorial of the fourth is 4 times the factorial of the third. And we know that the third is 3 times the factorial of the second. And we know the second is the 2 times the factorial. Oops, let me fix this. It's 2 times the fact of the first, which we know the answer is 1. So now we come back up, we get 1 times 2, which is 2, and now we come back up. 2 times 3 is 6, we come back up. 6 times 4 is 24, and we come back up. And 5 times 24 is 120, so the answer is 120. So we can see that this one is not that inefficient. There's no repetition in this process. The Fibonacci sequence has a lot of repetition. This is why it takes a lot slower. The reality is there's still a lot of math going on, so it's still going to be relatively slow. We run out of space quickly. But the idea is that the Fibonacci is significantly worse. So I think the takeaway for us today in this video is recursion is a powerful tool. We'll see some more examples, a lot of things that we've done. The 2 things that we're going to do that we haven't, that are important to see, are 2 things that we've already implemented. The binary search of a list of numbers, and the another sort called the merge sort, which is a really effective sort that's recursive. We'll see as 2 implementations of recursion that are really nice and have a benefit in terms of ease of understanding. But we'll stop here, and I'll see you in the next video.